Okay, let's dive into this. Welcome everyone to this explainer. Today we're taking a journey through one of the absolute most fascinating plot twists in the history of science. We're going to explore a true space-time oddity and discover exactly how a completely failed experiment ended up bending our very understanding of time and reality.
Think about this for a second. What if the most important scientific experiment in human history was actually a complete and total failure? Usually, we celebrate the experiments that perfectly prove a brilliant new theory. But today, we're looking at the famous Michelson-Morley paradox. We're going to uncover a profound, literally universe-altering truth that was hiding right inside what the scientists involved thought was just a massive, embarrassing mistake.
Section 1. The Great Aether Aunt. To really grasp what happened here, we've got to put ourselves directly into the mindset of late 19th century physicists. So those guys, the idea that empty space was just empty was completely unthinkable. No way. They firmly believed in this thing called the luminiferous ether, basically a supposed invisible medium that permeated all of space. And honestly, their logic made perfect sense at the time. Just like sound waves need a medium like air or water to travel to your ear, scientists naturally assumed light waves absolutely required this invisible ether to ripple through the universe.
So, to figure out how to actually measure this invisible stuff, they used what we can call the swimmer analogy. Imagine a swimmer in a river. If that swimmer is moving upstream, fighting against the current, they move slower relative to the riverbank, right? But if they turn around and swim downstream with the current, they move a lot faster. Physicists figured, well, since the Earth is hurtling through space in its orbit, it must be swimming through this ether, which should create a constant ether wind. They reasoned that if you measure the speed of light going against this wind versus going across it, the speed should be slightly different.
Moving on to Section 2. A famous failed experiment.
Enter two American researchers, Albert Michelson and Edward Morley. These guys became totally obsessed with finally catching this elusive ether wind. And the extreme lengths they went to for this are just incredible. Just look at their 1887 experimental setup. It was an absolute engineering marvel. First, they split a single beam of light down two perpendicular 11-meter paths using a series of mirrors. Now, to make sure random stuff, like passing horse traffic outside, wouldn't vibrate their delicate optics, they mounted the entire apparatus on a massive, super heavy block of solid sandstone. And the grand finale? They literally floated that massive stone block in a circular trough of liquid mercury. This let them rotate the incredibly heavy instrument with almost zero friction so they could test different angles against that theoretical ether wind.
Now, what's really interesting about this slide is the actual data they collected. It was absolutely shocking. Based on the Earth's velocity, they mathematically expected to see a fringe shift of about 0.4. But when they actually looked through the eyepiece of their crazy precise mercury floating machine, they got a measly 0.01. Basically, once you account for experimental error, the result was a 0. The light beams returned at the exact same time, no matter which way they turned the block.
This became famously known as the null result. And honestly, Michelson hated his own incredibly accurate data. He thought his life's work was a total dud. He wrote all these letters to his colleagues talking about how deeply disappointed he was, completely oblivious to the fact that this specific failure was about to change the trajectory of physics forever.
Which brings us to Section 3. Enter Special Relativity.
See, this failure wasn't a mistake in their sandstone and mercury setup at all. It was actually a fundamental, baffling truth about how our universe operates, just screaming to be discovered. Enter a young patent clerk named Albert Einstein. He looked at this stubborn null result completely differently. He later famously stated, "If the Michelson-Morley experiment had not brought us into serious embarrassment, no one would have regarded the relativity theory as a halfway redemption." Einstein basically realized the ether didn't exist at all, and to make sense of the experiment, he needed an entirely new framework for reality.
He built this new framework on just two straightforward postulates. First, the laws of physics are identical in all non-accelerating frames of reference. Okay, makes sense. But the second one is where things get wild. The speed of light in a vacuum is exactly the same for all observers, regardless of their velocity. So the crucial point here is light simply doesn't care how fast you are moving. Its speed never, ever changes. It absolutely does not act like that swimmer in the river.
Section 4. The light clock trained.
If the speed of light is completely and totally constant for everyone, everywhere, some very weird things have to happen to the rest of reality just to make the math work out. So we're going to deduce the core of special relativity right here, step by step.
And don't panic, there's no intimidating calculus required. We're using a beautifully accessible, math-friendly visual derivation approach inspired by the work of Zion Eligency, published in Celea Wa Publications. It's a fantastic way to visualize exactly what Einstein figured out using just basic geometry.
Imagine you are standing on a train platform watching a glass train zoom by at a constant velocity. Inside that train is a light clock. A stationary light clock measures time by just bouncing a single pulse of light straight up and down between two mirrors. Tick, tock. Simple enough? But because the train is moving past you, you don't see the light just bouncing straight up and down in one place. To you, the stationary observer on the platform, that moving light pulse must now travel a longer, diagonal path to hit those moving mirrors as the train glides forward.
Let's move 2 and see how this builds. If we map this out, it forms a shape we all learned back in high school geometry, the Pythagorean theorem. The diagonal path of the light forms a simple right triangle. We have the clock's vertical height, the horizontal distance the train just moved forward, and the hypotenuse. That's the long diagonal path the light actually traveled from your perspective on the platform.
Now here is where the ultimate paradox hits. The diagonal distance is clearly longer than the straight up and down distance. In normal everyday life, if a path is longer, it takes more time, or you have to go faster to cover it in the same amount of time, right? But remember Einstein's ironclad rule? The speed of light, c, absolutely cannot change. It literally cannot speed up to cover that longer diagonal distance, so something else has to give.
If the speed of light is perfectly constant and the distance it travels is longer, the only variable left in the equation that can change is time itself. And this brilliantly illustrates the concept of time dilation. Because the light has further to travel but can't speed up, the tick-tock cycle of the moving clock literally takes longer to complete from your perspective on the platform. For an observer in an inertial frame of reference, a moving clock will genuinely appear to tick slower than a stationary one. Space and time literally bend to protect the constant speed of light.
Section 5. Why this matters today.
Now you might be wondering, okay, that's a fun philosophical mind-bender, but does this actually affect me in the real world? Well, let's bring these space-time oddities back down to Earth. There are surprising everyday phenomena, like the way industrial electromagnets work, the cathode ray tubes inside old box televisions, even the distinct yellow color of gold, and the fact that the mercury Michelson floated his experiment in is a liquid at room temperature. All of these actually rely entirely on the subtle, relativistic effects of time dilation and length contraction happening way down at the atomic level. Actually, scratch that. It's not even subtle. If relativity weren't real, gold would just look exactly like silver.
But perhaps the technology we are most reliant on today is the Global Positioning System, or GPS. GPS precision relies absolutely on incredibly accurate atomic clocks placed inside fast-moving satellites orbiting the Earth. Because they are moving at high speeds relative to us down on the ground, time dilation is actively occurring up there in orbit. Those satellite clocks are literally ticking at a slightly different rate than the clock right there in your smartphone.
To put that into perspective, if engineers didn't program your phone to account for Einstein's time dilation, the satellite clock precision would drift by 20 to 30 nanoseconds every single day. That sounds microscopic, sure, but because light travels so insanely fast, that tiny time drift translates into massive distance errors. Without relativity, your GPS would completely fail and guide you miles away from your destination within minutes. It is only by actively applying mathematical corrections based on these universe-bending principles that we maintain pinpoint accuracy.
So, we started with two scientists staring at a frustratingly stubborn experiment floating in a pool of mercury, and we ended up uncovering a universe where time itself literally slows down just to keep the speed of light constant. It really leaves you with a profound thought to ponder. If time bends to keep the speed of light constant, what else about our everyday reality is just an illusion of our perspective? Keep that in mind the next time you check your GPS. Thanks for joining me for this explainer, and keep questioning the universe.